Good afternoon, everybody. As our test is fast approaching, I thought of conducting one extra lecture. Maybe few extra lectures will be required to cover the syllabus of Unit 1. So last class, we discussed few of the position sensors. Today we'll discuss Hall effect sensor. As you can see in the sketch, in the slide, when a plate is supplied with a DC supply voltage, the current starts flowing through this plate. And because of this flow of current, the charges are set up inside the plate. Now, as you can see, when this plate is influenced by the magnetic field, as you can see, the magnetic field set up by this magnet, when it comes closer, the charge lines are affected, and because of that, across these two faces, we have the voltage that is set up. Now this voltage is set up because of interaction between these electron flow, which is because of the current flow, or which is because of the supply voltage. And when this is affected by this magnetic field set up by this magnet, when I bring this magnet closer, this will be affected by this magnetic field, and because of that, across these two faces, some voltage is set up. Right now, this voltage is called as the Hall voltage, and this effect was discovered by the scientist Hall, hence the name Hall effect. Now, this fact of effect of magnetic field on the Hall voltage is utilized in various mechatronic applications. Now, these mechatronic applications vary from level measurement applications to position change measurement applications, like that. In various applications, these are used. Let us try and understand the Hall effect proper, and then the principle of operation of Hall effect transducers or sensor and its application. When a beam of, just listen to me very carefully, when a beam of charged particle passes through a magnetic field, forces act on the particles and the current beam is deflected from its straight line path. Thus, one side of the disk will become negatively charged and the other side will be of positive charge. This charge separation generates a potential difference, which is a measure of distance of magnetic field from the disk carrying current. Now, when you read it once again, you'll understand the concept. The application is a typical application of Hall effect sensor is the measurement of fluid level in a container. The container comprises of a float with a permanent magnet. When it's stopped, the electric circuit with the current carrying disk is mounted in the casing. When the fluid level increases, the magnet will come close to the disk and a potential difference generates. This voltage triggers a switch to stop the fluid to come inside the container. So it's a liquid level controller as well. So just let us see the sketch. What I'll do is I'll just invert it back, try to see it in an inverse way. Let us say this is the float, and at the top of the container, I have this plate with the supply voltage, which is fixed at the top. And whatever float I have, and I have a container with a fluid level. As the level rises, I have a float with this magnet. I have a float with this magnet. Try to look at it in an inverted fashion. Okay. This magnet is in the form of a float, right? So as the liquid level increases, the float rises up. And as the float has this magnetic field, magnet attached to it, as the level rises, this float, and in turn this magnet comes closer to the plate. And because of this, the magnetic field starts affecting this plate. And because of that, across these faces, I have the Hall voltage that is set up. And that is measured. And that voltage generated is directly proportional to the distance. Okay. When I set up my controller in the form of set Hall voltage, once this float comes closer, and when that voltage, the Hall voltage that is developed inside this plate crosses the predefined value, then I have the external circuit which will trigger, or which is connected to a relay which closes the valve, so that this level, liquid level, will be maintained. And this is how it can be used as a liquid level sensor. Okay, let us move further. Variable reluctance type velocity and motion sensors, and photoelectric type velocity and motion transducer. We will see one by one these two transducers. It's my velocity and motion transducer. Two types, because there are many types available. Out of those many types, we'll be considering variable reluctance types in the first place, and then photoelectric type secondly. This, as I said, these are motion sensors once again, particularly velocity sensors. We have variable reluctance. Now, reluctance is the term related with magnetic field once again, right? So I have a magnet, I have electric coil, I have an electromagnet, so to say. When it is supplied with the voltage, it will set up its own magnetic field. Okay. A magnet in the sensor creates a magnetic field. Now, as a ferrous object moves by the sensor, the resulting change in the magnetic flux induces an EMF in the pickup coil. Let us see. This is a target gear whose RPM is to be measured. This is rotating continuously. Now, this is my variable reluctance sensor. Because as the supply voltage is given, it will have its own magnetic field. When the ferrous object comes closer to this sensor, comes closer to this magnetic field, the magnetic field is set up by this variable reluctance sensor. The air gap changes, and as this magnetic field or magnetic flux, these magnetic flux lines are affected by the ferrous rotating object. Because of that, some electromotive force EMF is induced in the external circuit that will be measured. So that EMF is the direct measure of the rate at which this magnetic field is cut. Now, this rate means rate of change of angular position or rate of change of air gap. This rate of change of air gap is converted into rate of change of voltage, electromotive force. So this is how the variable reluctance type of a sensor can convert my velocity signal into some voltage signal. This is invariably used in many applications. Used to measure speed and or position of a moving metallic object. The necessity is that it should be a metallic object. And it should be able to interrupt or disrupt my magnetic field that is set up by my sensor. Sense the change of magnetic reluctance analogous to electrical resistance near the sensing element. It requires conditioning circuitry to yield a useful signal. So this is how we can describe variable reluctance sensor. But the second type of velocity sensor is photoelectric pickup. Once again, you have a disc with some perforation, with some holes on the periphery, and this disc is mounted on the shaft, which is continuously rotating. And I'm interested in measuring the RPM of this rotating shaft. Okay, I have the light source, and on the other side, let us see, I have a light source and I have a photoelectric sensor or photodiode, let us say, right? So I have a receiver, photoreceiver, and I have a light source. As this disk is rotating continuously, the disk with some holes along the periphery of this disk. Now, when the light passes through the holes, I have the light sensor generating the voltage pulse. And when the light does not pass through this ports, so in this region, if the light is not passing, then there will be no pulse. So I have corresponding to revolutions per minute, I'll be having pulses per minute. Okay, so it consists of an opaque disc mounted on the shaft whose speed is to be measured. The disc has a number of equispaced holes around the periphery. On one side of the disc, there is a source of light, while on the other side there is a light sensor, a photosensitive device. It generates pulsed output proportional to the speed of the rotating shaft. So my RPM is converted into pulses per minute, or RPS, revolutions per second, into pulses per second. Okay, so this photoelectric pickup also converts my velocity, angular velocity signal into pulsed output voltage. So both these sensors are used in the industry. Wherever I want to measure the RPM, even in our laboratories, we have in the IC engine laboratory, we have two IC engines. We have two-stroke engine and four-stroke engine. We have variable reluctance type of a velocity sensor or RPM sensor, and we have one photoelectric pickup type of a velocity sensor as well. We'll move to the next transducer, that is force transducer, or the sensor transducer capable of measurement of force. And in particular, we'll be studying strain gauges. Now, as the name indicates, the strain gauges, as I said, can measure forces. Now, these forces, when these forces are acting on a elastic member, elastic element, or elastic member, because of this force, there will be some stresses induced on this specimen, and because of the stresses, we have the strains also, surface strains also induced on the loaded material. Suppose I have a cantilever beam fixed at one end and applying load on this beam, and because of this application of load, what is happening? Because this beam is elastic in nature, it will be bent because of the bending stresses, and because of the stresses, this material, beam material, try to resist these bending stresses. And if I measure the strains on the surface, top surface as well as bottom surface, there will be strain change. On the top surface, I'll be having tensile strain, and on the bottom surface, I'll be having compressive strain. Right? So what is happening here? The force that is applied is first of all getting converted into, on this beam, is getting converted into the stresses induced in the material. And because of the stresses, we have the strains those are induced. And by Hooke's law, and for elastic materials, stresses and strains are proportional to each other. Isn't it? Stress is proportional to strain, or strain is proportional to stress. We have the elastic curve in third year design engineering. You must have studied. For in strength of materials, we have studied. We have stress and strain, stress on y-axis and strain on x-axis. Right? We have Hooke's law says that stresses and strains are proportional, right, up to elastic limit. Thereafter, the material goes into a permanent deformation, and ultimately it breaks, right? The strain or the deflection is zero thereafter. It is reduced, isn't it? Now, this property of the material. So, what is happening here? If I'm able to measure the strain, surface strain on the elastic member, I can convert that measured strain into stress if I know the modulus of elasticity of the material, because modulus of elasticity E is equal to stress upon strain. If I know the modulus of elasticity E, and if I know the strain, I'll be able to find out stress, because stress is nothing but E into strain. Strain I am measuring, E I know, So strain into E gives me stress. Now what is stress? Stress is force upon area, isn't it? Area is fixed. I know the area. If I know the cross-sectional area in which across which the stresses are induced, I'll be able to find out. I'll be able to find out force, isn't it? So stress is equal to force upon area. Stress I have already calculated. Stress into area will give me the force, isn't it? That's how the strain gauges are capable of measuring the force, though not directly, but through measurement of strain, and through measurement of strain, I'll be able to calculate stress, and from calculation of stress, I'll be able to find out, knowing E, I'll be able to find out what is the value of force. So this aspect of elastic material is utilized through strain gauge. Now, what is a strain gauge? As you can see, I told you what is the significance of measurement of strain, how the measurement of strain can help us in measurement of force, isn't it? And that's why strain gauges are capable of being used as force transducers. What are these strain gauges? Now, strain gauges are of number of types. Out of that, we'll be considering only electrical strain gauges. Now, these electrical strain gauges, as you can see one sketch here, this is a very thin wire of which the strain gauges are made. Now, this is actually the foil that is shown in the picture. I'll be having the thin wire to the tune of micron millimeter diameter, the thin wire, and those are formed in the shape of a spring, so to say, in the form of a coil, right? And these thin wires are provided with some terminal endings through which I can connect the electrical wires, and these conducting wires, electrical conducting wires, which are the resistance strain gauges, right, are used as strain gauge elements. Now, these strain gauge wires being fragile and delicate, you cannot handle it. So for that, they make use of the thin paper sheets used as a backing material. I have a strain wire, I have top paper sheet, and I have one bottom paper sheet. So it provides me a sort of a support to my strain gauge, electrical strain gauge wire, isn't it? Otherwise, I cannot hold it. Those can break, isn't it? And if I sandwich that strain gauge wire between the backing papers, it is having some rigidity, so to say, some strength, isn't it? Right? So this is the case of my electrical resistance strain gauge. Now, how these electrical resistance strain gauges can be used as strain measuring element, isn't it? Friends, as we know, what is strain? Strain epsilon is equal to change in length upon original length, right? Now, if we consider this conducting wire, using which I have prepared one strain gauge. When the conducting wire is subjected to strain, remember this strain gauge will be mounted on the elastic member whose strain is to be measured. Just try to recall the example I just quoted. I have a cantilever beam on which the load is acting, point load is acting. Because of this load, there are bending stresses induced in the beam, and because of the bending stresses on the surface of this beam, I have surface strains. What is the strain? Strain, I have got some change in length with respect to some original length, isn't it? So change in length on the top surface and on the bottom surface. And on this top and bottom surfaces, I'll be mounting my strain gauges. Now, because of the force, because of the stresses induced, I have the strains. That means I have got some change in length. Now, this change in length, when I mount my strain gauges, electrical resistance strain gauges, on this top surface, that those strain gauges are also, rather, these are bonded on the surface so that they become integral part of each other, isn't it? So the strain gauge becomes integral part of the beam, right? So the strain gauge behaves the same way as the elastic material behaves. Okay. If there is surface strain on this beam material, there will be surface strain there will be strain in the electrical resistance strain gauge as well. Okay, so whatever change in length the surface is undergoing, the same change in length the strain gauge material also undergoes. Okay, now let us come back to the original property of any conducting material. The electrical resistance of a wire having length L and cross-sectional area A and resistivity rho. The resistance is proportional to resistivity. It is directly proportional to resistivity, directly proportional to length, and inversely proportional to cross-sectional area. This is the property of any conducting wire. The resistance of that conducting wire, if resistivity increases, its resistance increases. If its length increases, its resistance increases. If its cross-sectional area decreases, resistance increases. So this change in length property is utilized in the strain gauge. If there is increase in length means there is some tensile strain. So corresponding to tensile strain, I'll be having increase in resistance of this conducting wire. And when there is compressive strain, and when there is reduction in length, I'll be having, when there is reduction in length, we'll be having reduction in resistance. So if I call this as delta R, so delta R will be increasing if the length is increasing, and delta R will be reducing when length is decreasing. Or if I subject these strain gauges to tensile strain, that's increasing length, tensile strain is increase in length. Tensile strain, I'll be having increase in resistance of this resistance strain gauges. And when it is subject to compressive strain, there will be decrease in resistance of this conducting wire. Now, when the wire is stressed longitudinally, R undergoes a change. Passing small amount of current through such wire will thus help measure voltage changes. If I connect this strain gauge to some external potentiometric circuit or external circuit where is some supply voltage is given, and as I said, when this strain gauge is subjected to tensile strain, there will be increase in resistance. And in the external circuit, I have some current flowing in the external circuit based on the original resistance of the strain gauge, isn't it? And this V will be equal to I into R. As R increases, the voltage increases. As R decreases, the voltage decreases. So I can correlate the material strain or the strain induced on the specimen material. I can convert it into strain induced in the electrical strain gauge, and that strain induced in the electrical strain gauge is converted into delta R, the change in resistance of that conducting wire. And this change in resistance is ultimately, if I use external circuit, it will change. This delta R will be converted to some delta V. So this delta V is proportional to delta R. Delta R is proportional to epsilon. Epsilon is proportional to sigma, that is stress. Stress is proportional to force F, isn't it? So this force F will be ultimately translated in the form of delta V. Right? How? We'll see one after the one by one. So passing small amount of current through such wire will thus help measure voltage change. The sensing element of the strain gauge is made of copper nickel alloy foil. In case of foil type strain gauge, there are various types of strain gauges. We have wire type strain gauge, and we have foil. Foil means sheet, which will be having certain breadth. थोड़ी strength देण्यासाठी त्याला those are some widths is there. Those are made. These are stamped out of the copper nickel alloy plate. The stamping करून it is given this kind of shape, which appears like a coil. We call it as a foil type strain gauge. So there are a variety of types. We'll just understand the principle of operation. The alloy foil has a rate of resistance change proportional to strain with a certain constant. Okay. Strain gauge type, we have got semiconductor strain gauges, we have got thin film strain gauges, we have diffuse semiconductor strain gauges, we have bonded resistance type strain gauge. Just now what we saw is bonded resistance type strain gauge. What is the selection criteria? Operating temperature, because temperature has effect on the strain. and the resistance of the material, the resistivity of the conducting wire changes with respect to temperature. So operating temperature also decide which type of strain gauge I should use. Nature of strain, whether it is a longitudinal strain, whether it is compressive strain, whether it is normal strain, right? What is the state of stress and what is the state of strain? So if I got uniaxial stress system, stresses induced only in one direction, or I have got biaxial stress system, stresses are induced both in x and y direction. Whether I have got triaxial stress system, the stresses are induced in three coordinate directions, x, y, and z. In such cases, in uniaxial systems, uniaxial stress system, I make use of simple wire type, bonded wire type resistance strain. In case of biaxial and triaxial stress system, I go in for something called as strain gauge rosettes. As you can see, yeah. In this sketch, I have got X, this strain gauge measures stresses in X direction, this strain gauge measures stresses and strains in Y direction, and this measures the stresses in Z direction. So this is called as strain gauge rosette. This is strain gauge rosette, right? I have got star type of arrangement. I have got right. This is also star type of arrangement. There is one more arrangement called as delta type of arrangement. So the selection of strain gauges for particular application depends upon the nature of strain I want to measure. Whether I want to measure uniaxial strain, biaxial strain, or triaxial strain, and what are my stability requirements. म्हणजे dynamic requirement जर असेल तर I need to use appropriate strain gauges which are capable of measuring dynamic strain. If the loaded member is subjected to stresses or forces not varying with respect to time, म्हणजे static arrangement असेल तर I need to select appropriate strain gauges for static strain measurement. Let us go a bit of details into bonded strain gauges, right? The same bonded resistance type of strain gauges. Either I have a coil type of a strain gauge or I have got a foil type of a strain gauge. These are the end connectors, right, which are connected to my external circuitry, right? This should also be connected, of course, and I'll be able to measure this change in resistance in terms of change in voltage in the external circuitry. Now, when this strain gauge is subjected to tensile strain, the resistance increases because there is increase in length. As there is increase in length, there will be increase in resistance. Now, in compressive, right? Compression, so decrease in length, decrease in length is compressive strain, will be decrease in resistance. Now, these are the axial direction, isn't it? In lateral direction, gauge insensitive to lateral forces. Yeah, these lateral forces or lateral stresses are not sensed by this strain gauge, right? त्यामुळं Poisson's ratio चा आपण इथे जास्त विचार करणार. Now, in case of biaxial system, where some lateral stresses are induced and where there are some lateral strains are also induced, I need to have a different type of arrangement for measurement of lateral strains. Okay. So the strain gauges to measure the strain requires accurate measurement of very small changes in resistance. For example, suppose a test specimen undergoes a strain of 500 into 10 to the power minus 6. Now this 10 to the power minus 6 is replaced by calling it as a micro strain. Micro corresponds to 10 to the power minus 6. Let us take the case of a meter. Millimeter म्हणजे किती? 10 to the power minus 3 of meter, right? And then further millimeters a micrometer, another 10 to the power minus 3. So 10 to the power minus 6 corresponds to micro. And as I said earlier, strain does not have any unit. Why? Because strain epsilon is the ratio of change in length upon original length. Change in length in meter and original length in meter, it gets cancelled. It does not have any unit. But this ratio is indicated in the form of micro strain or mu strain. This is not a unit, it's just to show you the scale of the ratio. So this mu corresponds to 10 to the power minus 6. So instead of writing 500 into 10 to the power minus 6, they write it as 500 microstrain, right? A strain gauge with a gauge factor of 2, a strain gauge with a gauge factor of 2 will exhibit a change in electrical resistance of only 2 into 500 microstrain. That is 0.0, not 1. Okay, let us see this ratio called as gauge factor. As you can see in this equation, gauge factor is the ratio of gauge factor is equal to dr by r upon dl by l. This is not mu actually, this is epsilon. Epsilon by strain. Now this is strain epsilon. So gauge factor is the ratio of dr by r upon epsilon. And epsilon in itself is dl by l. So gauge factor is equal to dr by r upon dl by l. Okay. So let us say, as per this step, gauge factor is the ratio of change in resistance or unit change in resistance upon unit change in strain. Denominator लगा है epsilon है, right? So gauge factor unit change in resistance divided by unit change in strain. म्हणजे काय? थोडक्यात amplifying factor म्हणून 1 unit of strain change brings about 10 units of resistance change. Gauge factor किती झाला? 10. Isn't it? If 1 unit of strain change is bringing 2 units of resistance change, so the ratio becomes 2 upon 1, that is 2, and the gauge factor in that, isn't it? Is that clear? I think we'll stop for today.